Thank you. And many thanks to the organizing committee and the scientific committee for letting me tell you what a congruence is and why do I think that you should know. So the work is inspired by a series of papers which in the last about 7 years Gordon Plotkin with various co-authors published about quantitative algebras, which are algebras enriched in metric spaces, and the reason why they were interested were as a foundation for the formal semantics of stochastic programs. And the scheme of my talk is that I will speak about three universals. So, what is a congruence in an ordinary category? I'm sure you know, but I will remind you nonetheless because of the analogy. Then I will speak about concept enriched categories, which is not inspired by this computer science community, but is really useful and helpful in finding analogies. I hope you will see the concrete meaning of what I mean. And now, then I will speak about metric enriched categories and the algebras called quantum algebras. So, what is a congruence in an ordinary category? Well, I would say it's an abstraction of kernel pairs. So if you have a morphism, then a kernel pair is simply a universal morphism with respect to this property. In other words, a pullback of f with itself. And if we ask what is a congruence, we forget this morphism and look at this parallel pair and ask ourselves, so what is it that we can say without knowing f? Well, first of all, that it is a relation that is collectively monic. Secondly, that it is reflexive, symmetric, and transitive. Okay, so can you say more? The answer is no, because there are many important categories in which the opposite also holds. And in these categories you say that congruences are effective. So this means given a relation which is reflexive, symmetric, and transitive, it is already a kernel pair of some morphisms. Okay, so what is it? What happens when we come to order enriched categories? So instead of speaking about just kernel pairs, it's reasonable to speak about sub-kernel pairs of a morphism, and by that I mean that it is universal with respect to this inequality. In other words, a Lex pullback of f with itself. And when metric enriched categories are concerned, this will get a bit more involved because there is no one pair that makes what you want. But you can speak about an epsilon kernel pair for every non-negative real, and well, no surprise, it's a pair such that universal with respect to the property that the distance of these two morphisms is less or equal to epsilon. So, why are we interested? For example, because in the famous thesis of Will-Lobier, there are wonderful results that are not as famous as these algebraic theories. One of them is a characterization.
Jiří,
yes.
do you want to put epsilon strictly greater than 0? Or
No, thanks for asking. No, I don't.
including 0?
Including 0. So that, well, 0 kernel pair is a kernel pair. So there is nothing wrong with 0.
Because if it's true for 0,
Yeah?
it must be true for every epsilon.
No, 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 sorry. Let me thank you for clarifying things. I should have at least put epsilon here. So what I mean is, you give me epsilon, I will find epsilon kernel pair, and for example, 0 kernel pair is kernel pair.
Okay.
Thanks for the question. Yes, please.
You have a universal quantifier then that probably you don't want.
There is a universal quantifier in all these things. So I mean the universal pair such that this holds, here the universal pair that this holds now, of course, in the enriched sense, and here the universal pair that this holds again in the enriched sense.
Are you using generalized metric spaces?
Yes, thank you.
So they are
Well, please keep reminding me of everything that I want to say and didn't. So when I say metric, I mean what everybody else ever means by metric, except that infinity is allowed as a distance, and the morphisms. So the objects are these metric spaces. Morphisms are the non-expanding groups. Okay, so I wanted to remind you of Lovier's thesis, namely one of it's the chapter 5 in his thesis characterizes varieties in the classical sense as abstract categories, and if you do not remember what a variety in the classical sense is, I prepared the only slide, so to say, that I really I didn't have much luck. I prepared it twice because a nice organizer swiped it very cleanly. Okay, so when I say signature, I mean the most classical thing. Yes, please. You have any question is welcome, as you have already noticed.
You assume symmetry. You assume symmetry in the metric spaces.
I said that a metric space is what everybody else, except category theorists, called a metric space. The only exception is that infinity is allowed. So, yes, instead of long sentence. So when I say signature, I really mean like building the most classical thing, so simply a collection of sets of n-ary operations. When I write category sigma set, I mean algebras, sigma algebras as object homomorphisms, as morphisms. And now I'm trying to survive. Good. When I write sigma pos, I mean ordered sigma algebras. And there are authors in this room who assume that sigma algebras need not have operations which are monotone. I do. So the category has sigma algebras, posets endowed with monotone operations and monotone homomorphisms as morphisms. And when I write sigma met, I mean what Hopkin and company called quantitative algebras, and this means a metric space endowed with operations which are non-expanding. And here I have to say something about non-expanding, because metric spaces, unlike posets, are not Cartesian closed, but they are nicely closed otherwise. However, Hopkin and company mean non-expanding in this respect. The Cartesian product is a maximum metric source. I mean the categorical product. And they have good reasons, which are absolutely not clear from their papers, and that will be the conclusion of my talk today, if I don't talk too slowly. Okay, so back to Bill. Maybe I should already switch to more resources. He characterized varieties Aha, I didn't say what a variety is. I promised, and I didn't keep my promise. Not nice of me. Do I see pens here? They are certain. Yeah, of course. First time the table and then don't find pens. So, a variety, of course, is simply a subcategory of this category given by a pair of terms. So you simply take a finite set X of variables, you form the free algebra of terms, and instead of saying a pair, you write it like this, because it's good for intuition. Now it's clear what it means that algebra satisfies it. Whenever you interpret the variables and compute the terms, they are equal. Here, the corresponding concept is an in equation, but again terms from the same realm. Again, the notation is such that you already know what it means to preserve this. And Plotkin and company introduced quantitative equations, which are again pairs, but indexed with a non-negative real. And of course, to satisfy such an inequality means whenever you compute the terms, the resulting elements will have distance at most epsilon. Okay, so now that we know what is a variety, what is the theorem, well, I am not writing theorem in brackets here, because I am slightly improving it. So, essentially, it's from here. A category, now in this sense, ordinary, is equivalent to a variety if and only if it has the following properties. One is that it has canal pairs and their coequalizers. The second one is it has effective congruences. So every congruence is a canal pair of something. And third, that it has a regular generator, which has two additional properties. One is, I think, well known, namely, it's sufficient strong generator, but regularly projective. So I should mix it. Strong generator, which is regularly projective, which means that the home functor of G preserves regular epimorphisms, and one which is probably not well known, namely abstractly finite. Now, abstractly finite was invented by him years before Gabriel and Ullmann came with finitely presentable and finitely generated. And until today, it's a very valuable concept. I will tell you immediately why. But first, I will tell you what it is. So this means that if you give me a morphism from G to a copower of G by whatever set, then there exists a finite subset such that now you take the sub-copower with its canonical embedding, and as I said, for every morphism like this, there exists a factorization through a finite subcopower. Now, in sets, these are just those good old finite sets.
Could you please put the blackboard a bit higher?
You can say
Thank you.
Okay.
You can change the border.
Yeah, I'm not Poland. Okay, so I need to. Sorry about that. What does it I will try not to write at this real anymore. So that's how I answer your question. That's how I could. Yeah. In posets, not a great surprise. Every finite poset is abstractly finite. But not the other way around. Actually, it is sufficient that it has finitely many connected components like the real line. But where it is a real substantial difference is in this metric world, because no non-empty metric space is either finitely presentable or finitely generated, but every finite space is abstractly finite, but of course, again, not the other way around. Also, finitely many components are sufficient. So, for example, real line is its usual metric. So, back to this theorem. The good news is, once you have this one, you don't have to listen to the rest of my talk, because the theorems will be absolutely the same. And the bad news is, you should listen to the end of my talk, because I will explain to you that they are not quite the same. So, here we are in the poset enriched situation, and I should cite a paper by Jiří Adámek and myself, in Algebra Universalis last year, where we already presented a Liouville-like characterization of varieties of ordered algebras. So I am improving it now a bit by letting you know what a subcongruence should be. So, for anyone who read the paper of Kurz and Belleville about exactness of order-enriched categories, or the really substantial and pioneering paper by Wood and Gardner about the same topic now in very general setting, anyone like that can ask, why are you telling us? And the reason is that if you read these papers, you have to work a bit. If you hear to me, there is no work. So, in other words, my definition of congruence is really substantially easier than theirs. So, first of all, the question is, so now we have a pair. What properties would it have? Namely, it is certainly a relation. By now I mean, of course, not only collectively monic, but collectively order embedding. It is certainly reflexive. No way shall it be symmetric in general, and transitive. So we are almost there. We just need a slight strengthening of the concept of reflexive relation. Namely, a relation is order reflexive so here we have a relation where it is order reflexive so first of all, don't forget that R0 and R1 are not assumed to be comparable. But if you give me another pair and it is comparable, so if I have some S0, maybe like this, S0 smaller than S1, then it factorizes through the relation. And that all, this is what subcongruence is. So now we are near to characterizing varieties. I have to just define that subcongruence, why do I say subcongruence? Yeah, because after all, both of these papers are really good, and they already have the concept of congruence in order and which categories, and I don't want to make a competition, I just want to make a new concept. A subcongruence in an order and which category is simply an order reflexive and transitive relation. And if this sounds a bit abstract, let us have a look what it is when our category is poset itself. So you give me a poset, which is a set is I should have both. So my object A is my poset, and I ask myself, what is subcongruence? So first of all, it's anyways a relation. And so the first thing that it says, so if you take notation, let me introduce the second relation that is on the same set X, namely Z of all pairs given by this parallel pair. And it is a subcongruence if and only if this is transitive. That's very... and secondly, it's more than reflexive, namely, it contains the given order relation. So it's really a very concrete thing to have such a subcongruence. And now, from this description, it's very easy to say what is the co-inserter of a subcongruence in posets. Well, you simply prove the following properties of this thing. First of all, it is a pre-order. So this is not automatic, you have to work a bit, but it's true. Secondly, it contains, I already said, it contains the relation. So, if you now take the same set here, but this is pre-order, then of course you have an order reflection. So, quotient to the poset where you take this pre-order and mode it out with the obvious equivalence. X is smaller than Y is smaller than X. Let me call this Q, and the lemma, which is the basis for what I will say next, is since this pre-order contains a given order, we also have a monotone map from the given poset to Q. And this is it. So it is the coincidence. And now comes the theorem, which I hurry up to say so that I can indicate at least something about metric spaces, namely that if we shift this theorem here, so now K is an order enriched category, and the variety is of ordered algebras. So an poset enriched category is a variety if and only if kernel pairs and the co-equalized sexes, congruences are effective, and the only thing here is that here you have a weaker property, namely a sub-residual projective, which is, as regular epimorphisms are the co-equalizers of pairs, here sub-regular epimorphisms are the co-inserters of pairs. And in the not existing last minute, let me tell you what I would have liked to tell you in great details here. In 1 minute I can only say Yeah, well, here the subcongruences are a bit more technical, but very natural because you have so many epsilon Feynman pairs. At the end of the story, you will get a theorem which is completely analogous. And why do I find it exciting? Because the definition of Gordon, Plotkin and company seemed at the first time absolutely wrong. So why would you ever make algebras in a cosmos which is not Cartesian closed, but then have the operations non-expanding with respect to the Cartesian product? The answer is because that's exactly the right thing. The category is then enriched and the varieties are characterized like that, so they did it quite right. And if you would switch, you would get something that's not even metric enriched. Thank you for attention.
Thanks for the talk. Do your quotients and kernels give rise to interesting factorization systems as well?
Yes. Yes, they do. In all these three cases, you will get... this is a very good question. What are regular epimorphisms in varieties? Well, precisely the surjective homomorphisms. What are subregular epimorphisms in varieties of ordered algebras? Precisely the surjective homomorphisms. What are subregular epimorphisms, which I didn't even tell you what they are, in metric enriched setting? Again, the surjective homomorphisms, and therefore you will get immediately the factorization system, namely surjective homomorphisms and embedding of subalgebras.
In the metric setting, do you have many epsilons appearing at once? When you
Exactly. Thank you for your question. Here you simply have to work with a weighted collimate, but a very natural one. What is the scheme of the diagram? You simply take the linearly ordered set of all real numbers, and you take two components of it. And this scheme is a discretely ordered category. So the distance of all these pairs is infinity, and you get back your epsilon by using the weight. And then the weighted collimates of this weighted diagram play exactly the same role as kernels in the left-hand case and not kernels, coequalizers here and point inserters there.
More questions?
Do you have any kind of mechanism for finding what the right notion of kernel is, or do you just sort of guess?
I guess.
Yeah. Well, not good, but...
Well, you know, if one wants to have a mechanism, one cannot beat your paper with John, in my opinion. It wasn't even an attempt to do so.
No, but I mean, you always have to start with the shape of the kernel and so on, and that's the thing. It's like, where does it come from? It's kind of mysterious, right?
Yes. Yeah. It is.
Questions?
So, yeah, regarding the theorems here that you can characterize varieties, it seems quite a lot like the Giraud theorems for protein decoupled. So, so do you also imagine that you can characterize these varieties as some kind of free-sheet-like settings, and in particular also for the metric theorems?
I haven't thought of that, but it's a nice thought. Yeah, thanks for your question. The answer is I don't know.
Questions? If not, thanks again.